Now that we've got the definitions out of the way, let's talk about some theorems. Okay. If f is continuous on a closed interval, AB, then f attains an absolute maximum value f of c and an absolute minimum value f of d for some numbers c and d inside the interval. I talked about this in the last video just very briefly, but here's the deal. If it's continuous on a closed interval, then it will have an absolute max and an absolute min inside that interval, okay? It could be the endpoint, that's okay, the endpoints are included there. So let me just kind of briefly explain. The two parts that are needed for this are the continuous and the closed. So why are those two things important? Okay, well, if it's not continuous, then it can do something like this. Okay, so if it goes from A to B, it could go up, open circle, closed, right, down like that. So here is a way where the function cannot have an absolute max, okay? So if it's not continuous, then it kind of keeps going up to here, and you're like, remember, the limit is going to be this thing up here, but it's not continuous there. And so it never attains this point, and so that is not an absolute max, okay? This one would have an absolute min, but this does not have an absolute max. So that's why continuity is important. Again, we're talking about a guarantee. Why is the closed interval important? Well, I think that one's a little easier to recognize because you could have things like tangent on some interval, okay? So for a couple different things, if say we're closed on this side, at B, we could do a couple things. We could go like this, that would be the open interval, or we could go like this and have an asymptote. In either case, neither of those have absolute maxes. So the things that we need both of these to not happen. And the way we can guarantee these two situations to be out is to say continuous and closed. And if that happens, right, then what we are guaranteed is that there is some lowest point and there is some highest point in the interval somewhere, okay? Again, because if you start here and you can't lift your pencil, like in whatever you do, there's going to be a highest point and a lowest point. Okay. So let's talk a little bit more about local maxes and minimums and what exactly is guaranteed at those points. So Fermat's theorem says, if f has a local max or min at c and f prime of c exists, then what? Let's look back at this picture here. So here is a local min. What happens to the derivative at that point? Well, you can see that the derivative is 0 at a local min or at a local max. So what this theorem says, if it has a local max or a min and it exists, then it's 0. So f prime of c equals 0. And so this theorem does not necessarily work the other way around. If f prime is 0, it's not guaranteed to be a local max or min. Okay, just to draw a picture of, say, x cubed. All right, this one has a slope 0 tangent line right there, but it's neither a max or a min. So this does not work backwards, okay? This is like, if I have a dog, then I have an animal. Does that work backwards? If I have an animal, then I have a dog? The answer is no, okay? This only works one way. If I have a local max and it exists, it's gotta be 0, okay? Very good. Next, a critical point. Critical point or critical number. Critical number. Oops, sorry. Critical number of a function is a number c in the domain such that either f prime of c equals 0 or f prime of c does not exist. Okay, so critical points or critical numbers, I sort of call them this, even though the word number is a better word, okay? But I sort of grew up calling them critical points, so it's sort of lodged in my memory. What this is all about is if I have these are going to be the candidates for maxes and mins, okay? So if I have something like this, a function going up like that, and then down like this, okay? So this thing has, the derivative is 0 there, the derivative does not exist there, and the derivative is 0 here, okay? So the three candidates for max and min are that, and that, okay? Now, only these two are going to be relative max and relative min there, but these are going to be the candidates, okay? So when I want to find all my relative maxes and mins, I'm going to find all of these because I know that this behavior is what has to happen at local maxes and mins. Again, I'm not guaranteed, but I have to test them all right? So, next theorem. If f has a local max or min at C, then C is a critical point of f. Critical number of f. Okay, so again, this theorem only works in this direction. So if local max or min, then it's a critical number, okay? And so this expands Fermat's theorem a little bit. Fermat's theorem says max or min and the derivative exists. And so now we're just kind of including, well, what if it doesn't exist? Okay, well, those are also points where we could possibly have a max or a min, okay? Again, I already talked about this. The converse of this theorem is not true because, say, x cubed, again, this is not, this is a critical number, but it is not a max or a min. Okay. So now we're going to spend some time finding critical numbers, essentially, okay? And so let's just get some practice at this. Example 119 here says, find the critical numbers of this yucky polynomial. So let's do it. How do I find critical numbers? Well, you take the derivative. Take the derivative, that's going to be 30x to the fourth plus, let's cheat a little bit here. Clear, quit 3 times 33. 132. X cubed minus 90x squared. And now I have to factor this thing. Okay, so again, critical numbers, I'm looking where the derivative is either equal to 0 or does not exist. Now, essentially, as I recall my teacher saying, when you're dealing with functions in this chapter, you're essentially going to take a derivative and set it equal to 0 on basically everything, okay? So that's what we're going to do on essentially every problem. This doesn't have any kind of place where it doesn't exist, so all I have to worry about is where it equals 0. I know I can factor out an x squared. What else can I factor out? I think I can factor out a 6 from each of those. What is 132 divided by 6? That's 22. Okay, so let's take out a 6x squared, and that will be 5x squared plus 22x. What's 90 divided by 6 plus 15? Ew. Okay. So those don't look like they have anything else in common. We can very easily say that this means that x equals 0. And the other one looks like it might factor. I'm just going to cheat a little bit because I feel like cheating. 5x squared plus 22x plus 15. Let's just take a look at a graph and see what we see here. Okay, those are not great numbers. All right, so it didn't factor. We'll just go ahead and do the quadratic formula. So critical number right there. So then x is equal to negative 22 plus or minus square root 22 squared minus 4 times 5 times 15 all over 2 times 5. And we'll just kind of leave this alone here. Let's cheat. On 22 squared minus 4 times 5 times 15, that's, did I do 2 squared? Oh, 22 squared. 22 squared minus 4 times 5 times 15 equals 184. Root 184. That simplifies, but I don't want to do it. Okay, so here are my critical numbers. X equals 0 and x equals that thing. Very good. Let's do a couple more here. How many more do I have? I have 1, 2, 3 more. 3 more. Let's just do these somewhat quickly here. Okay, let's find the critical numbers of this thing. And I'm going to note up front that this is x squared plus 1 divided by x minus 3, x plus 2. So the domain of this thing is x cannot be 3 or negative 2. And so if these come up and be things that look like critical numbers, they're still not going to be, because part of being a critical number is being in the domain. So here we go. F prime of x is low x squared minus x minus 6 d high minus high d low over square the bottom, and away we go. Now we have some simplifying to do on the top. That gives me 2x cubed minus 2x squared minus 12x. Now I have to FOIL this and then put a minus sign. So FOIL and minus. So minus 2x cubed, first outer, minus x squared minus makes plus x squared, first outer, inner, plus 2x with a minus, and last minus 1 makes plus 1. All over x squared minus x minus 6 squared. That is the best cancellation, because that means that this thing is going to factor a bit. Or I should say that I don't have to worry about the cube when I factor. That's what I mean. Squared and squared makes negative x squared. And then negative 14x. And then plus 1. All over x squared minus x minus 6 squared. Now, I'm going to go ahead and compute the discriminant of this thing. What is b squared minus 4ac? That is negative 14 squared minus 4 times negative 1. Yeah, okay, this thing has roots. Times 1. That is 14 squared to 196 plus 4 is 200. Oh, that's not so bad. 200. Okay, so this bottom thing, this derivative does have places where it does not exist, and it turns out that it's the same thing that I mentioned earlier. It's these points up here. So while those are places that the derivative does not exist, they're also places where the function does not exist, and so they aren't critical points, okay? This function has asymptotes at 3 and negative 2, so it doesn't have a critical point there, okay? It's got to be in the domain. As for where it equals 0, well, whenever you have a fraction equals 0, essentially what you're doing is setting the numerator equal to 0. And so to find the critical points, I just take the derivative and set it equal to 0 and say that negative x squared minus 14x plus 1 equals 0, which will be negative b plus or minus the square root of 200. I just did it all over negative 2. And that does simplify, and I don't want to. All right, so those are my critical numbers. I can't help it. So 200 is going to be 10 root 2. And that simplifies a little bit. 2 and 7, 5. So it's going to be negative 7 plus or minus 5 root 2. Now, when you do the negative and the plus or minus, so the negative distributed to here, which made it negative 7, the negative distributed to here, the plus 1 became minus, the minus 1 became plus, it's still plus or minus. Okay, so I don't need to do plus or minus negative 5 or anything like that. Okay, so those are my critical numbers, and I am good to go. These haven't been very pretty. Let's try a couple like this here. Find the critical numbers of 10x e to the 3 minus x squared. All right. F prime is the first times, the derivative of the first times the second plus 10x times derivative of e to the 3 minus x squared times the derivative of the top is negative 2x. Now, when you're finding critical numbers for functions that have an exponential component, what always happens on these is this exponential thing is stuck in every single term, and so you can always factor it out. So I can take out a 10e to the 3 minus x squared, and what I'm left with is 1 minus 2x squared, right? There we go. And so when I set that equal to 0, so there's my f prime. As I set this equal to 0, the exponential part will never be 0, right? E to the stuff is never 0, so all I have to do is do this one. So 1 minus 2x squared is equal to 0. So 2x squared is equal to 1. X squared is 1/2, so x is plus or minus 1 over root 2. And we're good to go. Again, this thing had domain all real numbers, so both of them are in the domain. Let's try another one here. So suppose I have x squared times ln 3x. So let's take a derivative. F prime is going to be 2x ln 3x plus x squared 1 over 3x times 3. Now that simplifies to 2x ln 3x. 3's cancel, 1x cancel, and I get plus x. And so here's my derivative. Let's set that equal to 0. And let's go ahead and factor out the x. That way we can do it. And I get 2 ln 3x plus 1. This says that x equals 0. However, the domain of this original function is x is more than 0. So that one's out. And all I have to do is worry about this one here. So what is 2 ln 3x plus 1 equals 0? 2 ln 3x equals negative 1. Ln 3x equals negative 1/2. This says that e to the negative 1/2 is equal to 3x. So x is equal to 1/3 e to the negative 1/2. And there is our lone critical point. Okay, I'll leave this last one to you. Go ahead and try that and ask some questions later. That's going to be the last one in this section here. In the next one, we will move on to how to find absolute maxima in the domain. Okay, see you then.